Okay, in this video we're going to look at circular motion. We're going to look at uniform and non-uniform circular motion. The difference is uniform circular motion means motion in a constant speed, and non-uniform circular motion means motion in a circle that's speeding up and slowing down. So the first case, the simple case, is just we have motion going in a circle, but the speed is constant. Now, this is going to actually represent an acceleration even if it's not speeding up or slowing down. Now, remember, when we talk about acceleration, that means one of three things. Speeding up and slowing down, that's mainly what we've been thinking about. When we think acceleration, most of the time we think speeding up and slowing down. But remember, acceleration, the definition of acceleration is that A is equal to the change in velocity over the change in time. But velocity is a vector, and acceleration is a vector. And so if we want to change the velocity, we can change one of two things. We can change the magnitude, and remember the magnitude of velocity is its speed. We can change its magnitude, or we can change its direction. And so if we're changing the magnitude, that's going to mean speeding up or slowing down. But changing direction, that means turning. And so we're going to now look at this last part, the turning. We're going to see how that impacts motion in terms of it being an acceleration. So let's recall a few things that we have talked about before. We know that when the acceleration is parallel to the velocity vector, that changes the speed. And when the acceleration is perpendicular to the velocity vector, that changes the direction. And the accelerations that are known, the accelerations that change the direction of the velocity vector, they're called centripetal accelerations. And we're going to see what that word centripetal means and why it's used in a little bit. So first of all, let's consider motion in a circle. So I have a circle here. It's going to have a radius. And of course, I've got radius vectors R1 and R2 pointing at different positions on the circle. And of course, we know the length of these two radius vectors are going to be the same because that's what makes it a circle. The radius is the same length all around. But these are radii, but they're also position vectors. And so we want to think of them as position vectors right now. And so we have a vector from the center of the circle to some point on the circle, and then this object is moving around the circle, so at some later time it's moved to the position R2, and it's got a velocity V2. Now, a couple of things to note about this. We are talking about uniform circular motion, so that means that the speed is constant. We're talking about motion in a circle, motion around a circle with constant speed. Notice the length of this green velocity vector and the length of that velocity vector are the same. That's because the magnitude of the velocity vector is its speed. Now, the direction of these velocities is different. So while this uniform circular motion means constant speed, it does not mean constant velocity. So the speed is what is not changing. But clearly the velocities are changing because they're pointing in different directions as this guy goes around the circle. And remember, when anything moves along a curved path, the velocity vector is always tangent to that path. That's a very important rule. And so we know this velocity vector is going to be tangent to the circle at the position R1, and that velocity vector is going to be tangent to the circle at the position R2. Now you might also remember, and this is going to be important in a little bit, that a radius vector and a velocity and a tangent line are always perpendicular. So this position vector, which is along the radius, is going to be perpendicular to that velocity vector, and this one's going to be perpendicular to that one. So these vectors make right angles with each other, just FYI. Now, since we have changing velocity vectors, that's going to tell us that we're going to have an acceleration. And remember, the acceleration is delta V over delta t. So let's calculate delta V. Now the first thing that we can do is we can draw the picture. And so if I've got this V1 and this V2, I can scoot them over here. Remember, we're allowed to move vectors anywhere on the page we want as long as we keep the direction the same and the length the same. And so I've moved my V1 here and my V2 here. So V2 points just to the left, V1 points up at this angle, and then I've connected them tail to tail so that I can do my vector subtraction. And remember, I want to do delta V, which is going to be the final minus the initial, and so it's going to point from the initial to the final. That's my delta V vector. That's the vector subtraction. And I can see the direction that delta V points. Now what I'm going to do is I'm going to take this delta V and I'm going to put it back on the circle halfway between R1 and R2. So if I go along this arc from R1 to R2 and I scoot this guy back over here, look at where it points. It points almost exactly at the center of the circle. And if you were to shrink this angle down, if you were to take the limit as this angle goes to 0, you would see that this vector lines up more and more towards the center of the circle. And so that's why this kind of acceleration is called centripetal. The word centripetal means center seeking. And so when you have uniform motion around a circle, that's constant speed motion around a circle, the acceleration that results from those changing velocity vectors actually is going to point towards the center of the circle. And since delta V over delta T is equal to A, and delta T is a scalar, remember when you multiply a vector by a scalar, it does not change the direction, that means that the acceleration has to point in the same direction as delta V. So the acceleration is going to point towards the center of the circle. Now we just looked at this construction, this triangle, delta V, which is formed by the subtraction from V1 and V2. We can do the same thing and we can get delta R. Now delta R is going to be the vector that points from the initial position vector to the final position vector. So I've scooted them over here so that we can look at it. We know this guy's gone over some theta. And so I've got R1's pointing at an angle, R2's pointing straight up. And then my delta R is the vector from my initial position to my final position. And that forms another triangle. Now there's one thing that may not be obvious. From the picture, it is obvious that R1 is going to swing up to R2 through some angle theta. But what may not be immediately obvious is that the angle between V1 and V2 must also be theta. Now why is that? Remember, we said that these vectors have to maintain a right angle. So from R1 to V1 is a right angle, from R2 to V2 is a right angle. And so what that means, if this guy tilts up an angle theta, this V1 has to tilt down that same angle theta. Hopefully that's clear and you guys can see that, because what that means is that the angle between V1 and V2 has to be the same angle as the angle between R1 and R2. And there's something else that's very similar about these triangles. This is a radius and this is a radius, so we know that that length and that length have to be the same. This V2 and this V1, we know that they have the same speed, the same magnitude. So this side and this side are also the same. And so what we can tell is that these have to be similar triangles because they have a side angle side congruency. We know that basically if you have two isosceles triangles with the same apex angle, they're going to be similar triangles. And so we can use the relationships of singular triangles to talk about what these magnitudes are. So let's recap what we have. We've got these two vector diagrams, which we have shown form similar triangles. And basically, we're looking at this delta V vector, which we know points towards the center of the circle. And so that's going to be related to the acceleration, which is called the centripetal acceleration. Now, the fact that these vector diagrams form similar triangles, what's the rule about similar triangles? The ratios of their sides are equal. And so if I do delta R over R, either one of these R's because they're the same, so I do delta R over R, that's going to equal delta V over V. And so that's what I have here. That's just the basic rule for similar triangles, that the ratios of the sides are equal. And so what I can do is I can take this V, multiply both of these equations by V to move this guy over to the left, and I get V times delta R over R equals delta V. Why did I do that? Because what I want is I want delta V over delta T. I'm trying to figure out what the darned acceleration is going to be. So I've isolated delta V. Now I can divide it by delta T, and that'll give me the acceleration. So I've done exactly that. I've divided both of these equations by delta T, and I get delta V over delta T. We know that's A. That's equal to V over R, delta R over delta T. And so this is what we have. The acceleration is delta V over delta T, and that's going to be equal to V over R times delta r over delta t. But what's delta r? That's the change in position. The change in position over the change in time, or the displacement over the change in time, that's the velocity. That's v. And so I can take this whole thing here and replace it with v. And so that whole thing will give me v times v. That's going to be v squared. And so I end up with the a is equal to v times v over r, or the acceleration is v squared over r. And this slide is basically the whole kit and caboodle altogether. Centripetal acceleration. When you have uniform circular motion is of course motion at constant speed, the acceleration always points towards the center of the circle. No matter where you are on the circle, the acceleration is always going to point towards the center. That's why it's called centripetal or center-seeking acceleration. So that's the direction. When you have motion in a circle, the direction is always towards the center of the circle. Now the magnitude of the acceleration is going to be the square of the speed divided by the radius of the circle. And that gives you the formula for calculating centripetal acceleration. Now let's extend this a little bit. Here I have a picture of effectively what would be like a roller coaster. I think in the United Kingdom they call it the Big Dipper, which I kind of like better, to be honest with you. But it's in the States, we call it a roller coaster. So anyway, this cart is moving down this roller coaster, and it's going around a curved path. And so it's doing one of two things. It's speeding up as it goes down, and it's turning. Now when it starts on the upward path, it's going to be slowing down, but it's still changing its direction, and so it's going to speed up on this side, and so the speed of this cart as it goes on the track of the roller coaster is constantly changing its speed. But at the same time, it's turning. So we have both types of acceleration. We have the type of acceleration that changes the speed, and we have the type of acceleration that changes the direction, which we call the centripetal acceleration. And so we can look at this picture and we can see here the velocity is always going to be tangent to the curve, and so up here the velocity is again tangent to the curve. And so we have part of the acceleration is along the velocity, and so that means it's going to be speeding up. Here on this path the acceleration is opposite the velocity, so that means it's going to be slowing down. But there's also a component of the acceleration that is perpendicular to the velocity, and we know that's the part of the acceleration that's making it turn. And so that's what we want to look at. This is called the general case. And it's called the general case because it's got both types of acceleration. The kind that makes it speed up or slow down, and the kind that makes it turn. Now what's interesting, even though this isn't exactly a circle, the part of the acceleration that makes it turn is still the centripetal acceleration, and it uses the same formula, v squared over r. But since this isn't a circle, it's a little unclear what the r is, and so that's what we want to see. Basically the idea is this. If you take the part of the curve that the velocity is tangent to and just take a segment of it, that segment would fit on a circle. That is, you could find a circle that would be just the right radius that it would match that curve. And so if I picked over here this part of the curve, it would have a somewhat different circle, a bit bigger circle that would fit. Basically, the flatter the curve is, the bigger the circle is going to be. And so the radius of the circle that fits the curve, that's the radius that we're talking about in this equation. And this is something that's actually called the radius of curvature. And you'll learn how to calculate this in Cal 3 or Cal 4, or one of the calculuses. I don't remember which one it's in. But actually calculating it is a little bit beyond the scope of this course, but you will learn how to do that later on. And so for now, you can just be given it. If you're given it in a problem, you should know it. You just plug it into the formula the same way that you would a regular circle. Now, let's just make note that the total acceleration is going to be the vector sum of the centripetal part, the part that makes it turn, the part that is perpendicular to the velocity, and the tangential part, the part that is along the velocity. Remember, the velocity is going to be tangent to the curve, so this acceleration component is also going to be tangent to the curve. And here I've done the parallelogram method of vector addition. You can see that the total acceleration is just AC plus A tan, and that's exactly what we have in our equation right here. And if you want to calculate the magnitude, you just use the Pythagorean theorem, and boom, Bob's your uncle. And you can get that very easily. If you want the direction, usually the direction is defined in terms of the angle to the tangential acceleration, because this is all defined by which way the velocity is going. So you go, basically it's the angle to the velocity vector that you make when you want the direction of the total acceleration. You usually define it that way, but as long as you're clear with how you're defining it, you could really define it any way you wanted, depending on what the problem was asking you for. But in any case, that's how you handle acceleration when something is turning.